All right, so let's get started. So we have been moving into multimodal optimization. Let me get this mouse out of the way. So this, we started about how for Pareto optimality, there's all these sort of methods for maintaining diversity and expanding diversity along the Pareto frontier once your algorithm has managed to crawl up and hit that frontier. So we talked about different methods for selection that try not to destroy diversity on the way to the frontier, but then how to actually create that diversity on that frontier. And multimodal optimization largely came out of people realizing that these types of diversity preserving methods could be useful for unit objective, single objective optimization as well. And so today we are going to be focusing on that. So so today's lecture is based on this niching methods and multimodal optimization. And a lot of what I'm going to be talking about here is summarized in a paper that I put in this unit by Singh and Deb from 2006. And so for more reference, so for more info, see Singh and Deb, 2006, on Canvas in this module. So, all right, so as we talked about before, we're working on this multimodal optimization. So what the heck is multimodal optimization? So the idea here is that rather than attempting to find a single global optimum, we are going to develop algorithms which attempt to find all of the local optima. So the focus here is population of output solutions that are spread across local and global optima. In other words, these are peak detectors. Now, there are a number of reasons why you might want to do this. And so sometimes it's actually just useful to have all other alternatives that themselves are interesting, local, they're sort of good in their own. So for example, let's just say, and this is kind of a cartoony example, but imagine if you had, some, number of some parameter that was like, and this is a little cooked up here, but imagine this would be like number of wheels. Well, of course, that could only be integers, but on a vehicle, and you have some performance here. Well, you could imagine that that of course there's no benefit to having a fractional wheel. So you could imagine that you would have these peaks in your optimization objective at 2 wheels, 3 wheels, and 4 wheels, and these and so there might be these kind of silly alternative designs that have, I don't know, whatever it means to be a fractional wheel, but you can see that there's these kind of local designs where you can say that even though the best vehicle you could build, might be the best vehicle has 4 wheels, it may be useful information to know that there is a pretty darn good 2-wheeled vehicle available. So this is a good 2-wheeled vehicle. And so if you were just optimizing over the whole design space, you might find just the best 4-wheeled vehicle, and that might be fine for you, but it's nice to know that you have a portfolio of other options that you could choose if sometime later on down the line, you find out that I'm in an application space where I really need, I can't afford 4 wheels on a vehicle, I'm constrained or something like that. Or there's other reasons why I might prefer a 2-wheeled vehicle, and then now I've actually got the best 2-wheeled vehicle as well. So it gives you a bunch of these different options. So that's one reason why you might prefer a multimodal approach to doing the search. The other thing that's nice about these multimodal optimizations is they generally lead to better global optimization, because if the algorithm has been designed to be sufficiently diverse to find as many peaks as possible and maintain small populations atop those peaks, then there's a good chance that it will have done enough exploration to find the global. So not only are you cataloging local optima. That's not how you spell cataloging. This would be cataloging. Was not a word I was planning on using. Not only are you creating a catalog of local optima, you are more likely to actually find the global optimum. Okay, so right. So, but in order to do this multimodal optimization, we need to preserve diversity, but we also have to, consider some, there's a bunch of different challenges that could occur here. So, for example, if I've got solutions that are over here and solutions that are over here, if I want to do crossover of those two solutions, because they're both kind of pretty high in fitness, if I do a crossover, am I going to get a bunch of infeasible solutions? And so another thing that can come out of these multimodal approaches is you can get these kind of restricted genetic operators, which are more guaranteed to kind of operate just within their niche. So I probably maybe don't want to cross over across huge amount. Well, I mean, I might, but in many cases, I don't want to do crossover across wildly different designs, because I'll go from, if I've got half of a hoverboard and half of a bicycle, together, those probably don't work together very well. I probably need the whole hoverboard or the whole bicycle. And so that particular crossover, I might want to cross over among the hoverboards and I might want to cross over among the bicycles, but I don't want to mix from those disparate designs. So these multimodal optimizations also, should allow for kind of, niches of local optimization. So you can have, like, for example, restricted crossover. And so, so that's kind of the optimal output will be something that will maybe have some of these things, will deal with this type of challenge. So these are ways in which we're kind of enhancing the standard genetic algorithm to just be kind of more effective at using the entire decision space. That's kind of what multimodal optimization really is. All right, so so in order to move from a standard GA to a multimodal we have to enhance a GA with a number of different niche preserving techniques. And we've already talked about basic versions of these that are employed in Pareto optimizing solutions. And so these are just kind of, and then even further elaborated to work under this single objective case. And so again, this is, these are surveyed in more detail in the Singh and Deb paper that I posted on Canvas. So just decide if I want to just jump right in here. And so hopefully these methods will maintain diversity over a large number of generations. That's kind of what we're trying to get at here. And so we've already talked a little bit about fitness sharing approaches. And so let's go a little bit farther in implementing or talking about the implementations of fitness sharing approaches. And as we talk about these different approaches for niche preserving techniques, I want you to be thinking about, these might be clever ideas, but how practical are they computationally? And that's something that we're going to see that we'll often see a technique be introduced as kind of a good idea, as in principle, but then it'll get modified to make it more clearly computationally efficient so that your algorithm doesn't take a huge amount of time just trying to calculate these niches. And so, so the first kind of simple idea here, which we've already kind of talked about a little bit, is you take whatever fitness you have and you do fitness sharing, where you're going to divide your fitness by your niche count. And so we have a shared fitness for strategy I, which will be its original fitness divided by a niche count, which I'm going to call N sub C, associated with strategy I. And now we have to figure out how to actually do this niche count. How do we count the number of individuals around this individual who are going to share their fitness with this individual? And so a simple way to do niche counting, and this is kind of a generalized perspective here, is I'm going to define a niche count as the sum over all individuals of this function S, which I will define in just a second here, which takes on the distance dij. This is distance between individuals I and j. And we can either calculate this distance either in the genotype space, in which case we might, for example, use the Euclidean distance xi minus xj, or we can calculate it in niche space or criteria space. And so in order for me to calculate it in criteria space, it's basically just calculating f, because I only have a single objective, f of xi minus f of xj. Where here I'm just saying, single objective, right? So either of these are possibilities. Generally, this is going to be better performance, or rather better outcomes. But it's going to be simpler often to just calculate the distance in the decision space. So for each individual I, we can then calculate how far they are away from every other individual. So already that sounds kind of costly, because if you have n individuals, you're going to have n squared connections between every individual and every other individual, and each one of those n squared connections is going to have an associated distance with it. So already we're kind of getting pretty costly here. Now, this S here, this function, maybe I'll put it in a different color. So S dij is just going to be a function 1 minus dij over a parameter, a hyperparameter, sigma share to the alpha. And I needed to give myself a little more space. So what I'm going to do is just put this on a different page. Maybe. There we go. All right, so this is continued from previous page. And I'll put over here, S defined next. Where we're going to say that dij is less than, for the case when dij is less than or equal to, I guess, this sigma share, which is a hyperparameter. And it will be 0 otherwise. And note that in the special case, so I'll say when alpha is equal to infinity, then maybe that's a terrible notation. Let me clean that up a little bit. So if alpha goes to infinity, then S dij is going to be equal to the, what I'll call the Iverson bracket, which I'll define in a second if you're not familiar. Which this is called the Iverson bracket. So just a convenient notation to mean that it is equal to 1 if condition true and 0 otherwise. So if I start with kind of this simple case, if you take alpha equal to infinity here, then all this Sij does is basically count. This is sort of keeping count of how many individuals are within this radius here. So if I go back and look at what this function is doing, it's just going to count up a scaled version. It's like, this is like a scaled count. And so it's going to go through every individual. And when alpha is equal to infinity, it says, are you within this sharing radius? And if you are, you get a 1. If you aren't, you get a 0. And so when alpha is equal to infinity, all this does is count up how many individuals are within some sharing radius. And so as a hyperparameter, I define the radius of a niche. So I just had to sort of say ahead of time that, in whatever space that I'm using, I'm going to define, 1 unit to be the radius of anyone who is within 1 unit of anyone else is in that individual's niche. And if alpha is equal to infinity, then all the niche count is, it's going to count up how many individuals are within 1 count of 1 unit of our focal individual. What this generalized function does is, by letting us set this to lower values of alpha, allows us to kind of taper the count based on distance. So those that are farther away take less away from the fitness than those that are close. And so what this is sort of doing here is, if the delta is equal to 0, then you get the full count. But if delta is somewhere between 0 and sigma share, then you get something that is slightly less than the full count. And so that way, I'm still only looking at individuals sigma share units away from me, but the ones close to the boundary are hardly going to add to the niche count, but the ones close to me are going to add 1 to the niche count. So it's just a way of scaling this up here so that my fitness sharing is going to be strongest nearest to me and weakest farthest to me, and totally 0 outside of sigma share. And part of the reason we define this sigma share is with this hard boundary here, is it hopefully reduces some of the computational burden because if there's some way that you've organized your points so that you can kind of keep track of roughly who's who's a farther, I mean, if you sort of have an ordering where you don't know the distances, but you know they're ordered in a data structure based on relative distance, then once you've calculated that there's a certain individual is kind of at, is beyond the boundary, then you don't have to keep calculating distances after that. So this provides at least potentially some computational savings where you don't have to calculate the distances for all individuals, only individuals that are sufficiently close. But then you've got to come up with some clever data structure that keeps track of who's sufficiently close. And those data structures do exist. The agent-based modeling community, for example, has those data structures that run underneath their system, so that when you have to ask an agent, what agents are within a certain radius of you, it can relatively quickly calculate that. So that's kind of the idea here for this kind of generalized niche sharing, where we're just dividing the fitness of the original individual by how many individuals are nearby, and we can scale what it means to be nearby by this function here. All right, so questions about that, this sort of simple generalized niche sharing. Yeah.
So we're calculating the idea, right, which is the distance between two genotypes.
Mm-hmm.
And then we're figuring, we're like applying that as a radius. But I guess my issue is like distances in multiple axes don't necessarily have the same kind of meaning. Like the difference between 1 and 2 wheels has a lot different meaning than like the distance between 0 and 1. Like
sure. And you are free to define your own distance metric. And so you could use like a Mahalanobis distance, for example. So there are other metrics other than the Euclidean metric that weight different dimensions differently. So I can define in multi-dimensional space, 1 unit of distance in whatever that, in general distance as being equivalent to 1 in this dimension, but 0.1 in this dimension.
So you want to apply like a transformation that makes like the sphere that we're doing make sense.
That's right. I mean, so that's if you do know ahead of time that you're going to value some distances more than others, you can apply weightings to those things, and those weighting. And so if you've ever in statistics calculated like a principal component analysis or doing those sorts of those techniques, that's basically doing the same thing where you're saying that like if I take a bunch of data, some of the data that I'm taking is going to have a lot of variance, and other data that I'm taking might have very little variance. And so really, when I look at variation in one dimension, I really care about how many standard deviations they are in terms of like the total variance. And so in many statistical applications, the first thing you do is transform all your data by their standard deviations effectively so that you put everybody kind of on a level playing field. And you can do that more generally with any type of distance metric. And so I've just put in the Euclidean distance metric here, kind of the L2 norm. And technically, if I were to do that, I'd put a little 2 down here. But you can put any distance metric you'd like in there, and that possibly rescales things. And you can actually scale things diagonally or whatever. So you can say like, if it's a mixture of this and this, then that's contributes more to distance than if it's either one of them alone. So yeah, those things are possible. Yeah.
So just to be clear on what you're saying, so let's say we're finding the norm of like we have 2 points, we have the vectors and dimensional.
Right.
We find the difference, that norm, rather than just adding the squares of each component, for one of the components, we could like double it or something if we want that distance to be more important. Is that what you're saying? Yeah,
right. So, I mean, I guess I can just draw this up here. So if I have like the 2 norm squared of 2 vectors, then those vectors might, I might write that out as this little dot product. But I can also define a different distance metric, and I'll just do it squared here, where I apply a matrix transformation in between. Oh. Something along these lines. And so, or maybe I actually meant to put those on the other side, but the idea is you can apply a matrix transformation in between or of your coordinates before you actually end up doing the squaring the components out. And so that's kind of like if it's, you know, if you thought about it as just diagonals, you could view it as scaling each dimension differently before putting them into the distance metric, but you can just do things much more general than that. So if you were to look up like, I'm going to spell the last name incorrectly, but Mahal Anobis, so very famous Indian mathematician. So if you look at like Mahalanobis distance, for example, that gives you an example of a very generic way to scale dimensions and still be able to calculate a norm in a very normal way.
You were talking about like you could scale a distance if it's like a mixture of those two.
Mm-hmm.
With those, you could be considered the off-diagonal elements.
That's right. That's exactly right. So yeah, so if this W matrix that is scaling these differences, you can think of that as the diagonal would just scale each dimension, but then any of the off diagonals would scale the mixtures of those dimensions and so on. Yep. All right, so any other questions about this general idea of niche counts, like methods for doing niche counts? Let me see, I think there's a question online. Just to clarify, when we say every individual, do we mean all individuals or only individuals in a niche when calculating niche count? So what we mean by, so technically this formula is defined over every individual, across all of them. But the scaling function here has this hard boundary at this sigma share hyperparameter. And that effectively makes it so that you're only counting those in our approximate niche distances away. So we don't know who's in our niche, but we're going to say our niche is 1 unit away in this distance metric. And so we're going to go through every individual and ask every individual, are you 1 unit away or less in our distance metric? And only then we count you. So there could be, again, if you've got fancier data structures that keep track of who's next to who, sort of topological based data structures, then even though you don't know the exact distance, the Dij, you might still be able to order them so that you can more efficiently do this calculation without going through every individual. But in principle, you're going through all in individuals and seeing how far away they are, and then scaling that so the ones that are really far away get killed or get not added at all, and only the ones that are this close get added to the count. All right, any other questions? Generalized niche counting. Okay, so an alternative we can do instead of counting is we can do an approach that is inspired by clustering, inspired by k-means clustering, for example. And so an alternative is to use clustering. So the idea here is we're going to introduce, and this can be much faster for large N. So given N individuals, those are all of our individuals, we are going to have some parameter of capital K, which will sort of be kind of like how many niches do we expect we're going to want to maintain in a population. So given N total individuals, start by taking the K, and that's another hyperparameter, best individuals as seeds for these niches. So basically seeds for K clusters. Or we can think of them as centroids of these clusters. So then we're going to, once we have all of them, then we have these two other hyperparameters. Distance minimum, dmin, and D max. And so what these two things are here are this distance min is our minimum distance between cluster centers. So this will affect choices here. And then distance max is our maximum distance between individuals in a cluster and their centroid. And then you typically, it's going to be easiest to do this in genotype space. If you can do this in the niche space, you probably will be better off in performance, but figuring out how to do the geometry in the niche space is going to be a lot more difficult than just using the decision space instead. So we use these parameters to adjust the cluster components and the number of clusters. So we can start out by taking the k-best and then try to do this, but then we might, based on the feasibility of this, these two here allow us to adjust number of clusters and cluster members. So we might find that all k individuals are too close together to be their own centers of clusters. And so we're not going to define k clusters. We might end up having to find only like one cluster. But we start trying to establish k clusters. And then we use dmin to filter those clusters, and then dmax to figure out what other individuals are in the cluster. And so what's nice about this approach is it partitions the space up in a way where counts don't have to be associated with individuals. Counts can now be associated with locations. So rather than having to calculate my count and your count and your count and your count, I just have to say, what cluster am I in? What's the count for this cluster? And that tends to be much more efficient. So I'll write that formally in how we do the niche count. Is this clear so far, what I mean by this? By creating these k clusters and adjusting these k clusters according to these constraints, which are hyperparameters. So we've got a k hyperparameter and these two distance hyperparameters. Doesn't look like there's questions online. All right, so now from here, I can calculate a shared fitness for every individual in the cluster based on a niche count, which is tied to the cluster and not necessarily the individual itself. And so we are going to define F shared for this case, and this will be for individual I, as the F original divided by, we're going to scale the number of individuals that are in that cluster. And so we're going to say that in C, this is the number of individuals in the cluster, in this cluster. So I could make it in CI, times a similar scalar as we had before. Oh, okay, this is going to be DIC divided by 2 D max, and that whole thing to the alpha. All right, so DIC is distance between individual and the centroid of the cluster. And so now, again, if alpha is equal to infinity, then this term goes away, and so I guess I could write this down if that's helpful. If alpha goes to infinity, then F shared I is just equal to F original I divided by niche count. So in the simplest case, we know how many individuals are in this cluster, and we're just going to divide every individual in the cluster. We're going to scale down their individual fitness by the number of individuals in the cluster. But if we want a little bit more fine-grained control of the niche sharing so that we don't penalize everyone the same, then we, rather than penalizing them all based on their individual distances to every other individual in their niche, what we do instead is we scale the niche count for that niche by the distance that individual is from the center of that niche. And so they use 2D max. I don't know why they necessarily, I mean, I know what their thought is that D max is a radius, and so 2D max is a diameter. But I never quite understood, and I never bothered to look it up, why, because DIC should always be less than the radius D max, unless I'm not thinking about something correctly here. And so it seems to me like they don't need this too, but it's just a constant, so it's not going to matter too much here. But the idea here is, you see, if you're basically on the periphery of a cluster, then this term is not going to affect you as much because you're sort of maximally distant from the cluster. You still get scaled down, but you don't get scaled down as much as individuals who are sitting right on top of the centroid of the cluster. And so that's how they calculate this. And it is much more efficient. It's far more efficient than the traditional sharing when n is large. Because there's a lot fewer individual to individual distances you have to calculate. All right, so questions about this clustering approach. It's kind of k-means inspired. You try to say, I want k clusters to begin with. You might have to, initially, that maybe that'll be very few, but then over time, what's going to happen is that the fitness of all those that are sitting on top of each other are going to go to 0. That's going to create new individuals farther away, and they'll establish their own little niches where inside their own niches, they'll get to keep all their fitness. And then that helps establish this kind of diversity. All right, any questions about that? Online, I think I see a new question. Yes, the centroid of the cluster is the seed. So if I go back here, the seed here is the same as the centroid. Any other questions? So another approach to do this diversity preserving or niche preserving. Now, how you choose that K is going to depend on the function. And so if you speculate that your function has got lots and lots and lots of peaks that you want to find, then you better set a very high K, and you might want to set a very high N. If you speculate that your function has got a couple of peaks, but you just want to make sure you get those couple of peaks, then you can set your K lower. So that K is a hyperparameter that's up to you, but it really depends on your kind of a priori knowledge about the function you're trying to optimize. Okay. And then likewise, dmin and dmax, if you have information about the resolution of these peaks, sort of like, well, we generally expect to find all of the peaks close together, or we expect to find there might be one local peak over there, another one far away in a very different design space over there, then you can imagine setting your dmin and dmax sort of appropriately. Okay. All right, so those are our sharing approaches. There are also a number of clearing approaches. And I've talked a little bit about clearing already. it's sort of a simple idea. The idea here is we're supplying fitness resources only to the best within a niche. So it's a very elitist strategy. So the idea here is step one, we're going to sort individuals by their fitness. And then take the K, again, this is another hyperparameter, best solutions. And then, so those end up being our elites. So now we're going to look at all those elites and we're going to see who's around the elites and then get rid of all their fitness. So in step two, we're going to find all solutions within some sigma clear distance. That's another hyperparameter of the K best, and set fitness equal to 0. And then that will cause them to be cleared in next round of selection. That's simple clearing. And then after that, 3, we repeat clearing so we repeat based on next K best. And we do that until all individuals considered. That's clearing. So you start with the top K, clear who's around them. You're going to be left over some others that still have non-zero fitness that are beneath those K. You look around them, you clear who's around them, and so on and so forth. And then hopefully you get these little fiefdoms where you've got these separated individuals that don't have a whole lot of individuals around them that all maybe are distributed along the peaks of your optimization objective. So that's basic clearing. And then we would typically do this in genotype space for simplicity. All right, so that's basic clearing. Any questions about that? I'll mention a modified clearing approach as well. There. All right, so that's the simple clearing. There are modified approaches. So for example, Deb and Singh, or Singh and Deb, have, a modified clearing, which they were, I think, trying to advocate for in this, in their article, but I think they end up finding it doesn't actually do much better, and it's kind of complicated. In modified clearing, which I'll summarize graphically, it's a similar idea, but you've got your individual and you kind of establish these spheres around it. So one of them is of distance r, and then we've got another sphere around it of distance, I think 2r or 1.5r, and then a final sphere. It's kind of like the 101, the 201, and the 101, the 202, and the 303. And then we've got a 2r that's farther away here. And the idea is that in modified clearing, when you do your round of clearing, you've got your focal individual here. If there's any individuals that are within this small distance, then they get cleared completely. Their fitness is set equal to 0. But in order to enhance diversity, then what they've done is they say if anybody falls in this middle area, then we are going to draw randomly some perturbations to their position to move them into this outer circle. So I'll draw in a little diamond here. So they just get moved as sort of a directed mutation. And then what they do is I think they actually have to do an additional round of clearing after this. Now, I'm not, all that really matters to me is that you basically understand the difference between sharing and clearing. I'm throwing this up here to show you that there are other maybe clever, maybe not ways that you could implement these things like clearing. I hope you can understand sort of the intuition that they were going for here. They're still clearing those solutions that are very small, but for those that are close by, then their hope is that some sort of also sort of like a cross between mutation and recombination. They're trying to create a little bit more diversity. So if you read their motivation, they feel that traditional clearing just throws away a lot of solutions. And so their thought is rather than defining a big clearing radius, like this is kind of the standard clearing radius, and throw everything away that's in that clearing radius, let's define a smaller clearing radius, throw everything away there, and anybody who happens to be in this outside area, just kind of move them a little farther away. So that was kind of their thought, is that maybe it's actually wasteful to throw away a ton of solutions inside a clearing radius when the ones that are on the periphery, you could just move out. So that was their thought there. But this movement is pretty costly computationally. You got to draw a bunch of random numbers and then perturb this thing. So it really would have to have a major payoff in order to be worth the extra complexity that you add here. And I think they end up showing that it's not really that much worth it. All right, so those are clearing approaches. And then I like to talk about crowding approaches, and then we can compare across them. So are there any questions about clearing? I see some questions online. So I see, why not use probability as we move away from the cluster, as we move away from the radius, clear less as you move away from the center. And so there's, you could define a more sophisticated clearing where you could do stochastic clearing, where individuals that are close by, you could immediately draw a random number where they have like a 99% chance of being cleared. This is an 80% chance of being cleared, a 75% chance, and so on. You could go on through there. You certainly could do that, but then that would mean for every individual, you're gonna have to calculate their distance from the center of this clearing radius and then draw a random outcome to determine whether to clear it or not. And that ends up adding up if you've got 1,000 solutions across 100 generations or 1,000 generations. So in principle, the idea is a good one to think about, but it ends up racking up a lot of computational cost over the length of the whole algorithm. And in the end, those sorts of approaches don't necessarily do much better. This is sort of an attempt at a compromise there, where you've got relatively simple clearing here, and then a little bit of a dislocation here that's trying to kind of feather the edge of the clearing radius in kind of a similar sort of way. But as I think, if you read the paper, this modified clearing doesn't really do that much better than standard clearing, and it is, I think, more costly. So I think a truly stochastic clearing approach would be even more costly, and so I don't think it would end up doing much better. But you're welcome to try that. That would be a great mini project, is to implement a multimodal optimization. You can even use the x sin x function that we use on mini project 1, see how many peaks you can find, and try clearing versus an alternative clearing approach that you'd like, either that you came up with or that you found in the literature. That would be a great mini project. Okay, so any other questions that came up there? I think that's all I saw pop up. Okay, good. Questions in class? Pretty clear on clearing? Okay. All right, so then the last thing that I want to cover here is crowding and restricted tournament selection. So these are additional popular ways to maintain and enhance diversity. Crowding and restricted tournament selection. All right, so how do crowding works here? So these are based on the ideas of competitive exclusion. Oh, I forgot, there's actually one more that we'll have to talk about after this, but be quick. So this is based on the idea of competitive exclusion. And so when you create offspring, those offspring are very often close to you. And so they kind of create a crowd. And so what a crowding approach does is it competes the offspring versus the parent, and whoever has the higher fitness gets to stay and the other one dies off. So does the offspring replace the parent or not? So, so the basic algorithm here is you perform n over 2 times the following steps. One, you select 2 parents I'll call them P1 and P2 without replacement. So that means that once they've participated in this, they don't get to participate in this anymore. And then 2, you do crossover. And I'll just say you do crossover. Well, okay, I'll just do it separately. So you do crossover, that creates a C1 and C2, and then you do mutation, and that creates a C1 prime and a C2 prime. And so those are our offspring, C1 prime and C2 prime. And then we either do deterministic crowding or probabilistic crowding, which relate to tournament selection or fitness proportionate selection, but in these like tiny little populations of parent and offspring. So in deterministic crowding, which is again, just basically a version of tournament selection, we say there's 2 conditions, and written out, these might look a little silly, but if you focus on them, it might make some sense. So if the distance between parent 1 and offspring 1 prime, plus, this is like a little triangle inequality type thing here, plus the distance between parent 2 and offspring 2 is less than or equal to the distance between parent 1 and offspring 2 plus the distance between parent 2 and offspring 1, then we're going to compete offspring 1 versus parent 1 and offspring 2 versus parent 2. We're just kind of determining the pairings here. So basically we're saying, this is sort of saying if offspring 1 is closer to parent 1 and offspring 2 is closer to parent 2, then compete 1 against 1 and 2 against 2. And so from here, then we're going to say in this condition, then we say that if the fitness of parent 1 is greater than or equal to the fitness of offspring 1, then we take replace C1 prime with P1. And then similarly, if the fitness of the parent 2 is greater than or equal to the fitness of the child 2, then replace child 2 with parent 2. And then in the other case, we just compare parent 1 to child 2. So in that case, if the fitness of parent 1 is greater than or equal to the fitness of child 2, replace child 2 with parent 1 if the fitness of parent 2 is greater than or equal to the fitness of child 1. Replace child 1 with parent 2. End. And so that's deterministic crowding. So it's basically tournament selection between parent and offspring. We can also do probabilistic. Any questions on this? I know the notation's ugly, but I hope it's clear that we're just saying we find out which parent-offspring pair are the closest, and then we do tournament selection among those close pairs. 2 tournaments, one with this pair, one with this pair. You get 1 winner in each. And then otherwise, you know, if so this is in the 1 pair. This is in the P1C1, P2C2 option. This is the P1C2, P2C1 option. But it's just finding the 2 parent-offspring pairs that are closest. That's it. All right, so that's deterministic crowding. We can also do probabilistic crowding. Which is basically fitness proportionate selection. And the idea here is that if you look at a parent and offspring, then you replace with probability f of x over f of x plus f of y. So, you know, I'll say for an XY pair, where this is a parent and this is offspring, so you can do the same sort of thing where you pair them up, but instead of taking the absolute winner, you do probabilistic. But you know, it's just sort of the same sort of idea. Both of these options, deterministic crowding and probabilistic crowding, have this unfortunate problem of niche loss. And what I mean by that is, so what is niche loss? And so what can happen is you've got your optimization objective, whatever, something like this, and you happen to have, you know, one parent. Let's say this parent was already sitting up here. This is P1, and we've got some other parent that's maybe over here, P2, and they end up having offspring. And so you end up, let's say you end up getting both of your offspring just due to recombination and mutation, just happen to be both over here. So this is C1 prime and this is C2 prime. Now what can happen is that if you happen to pair up P1 and C1 prime, actually drew these, let me draw C1 prime a little higher to make this point, to make this actually look like a feasible outcome. So I'm going to draw this peak higher. Okay, so now this is P2, and let's say this one down here is C1 prime. Now, if you happen to compete P1 versus C1, P1 gets killed, and the niche is lost completely. So if you happen to have a few parents being the sole members of a niche, then this tournament selection or even this probabilistic crowding has this effect where you can end up pairing individuals that span a large space across from each other and just destroying an entire niche. So this isn't so great. And so that's why the kind of solution to this end up being restricted tournament selection, which really basically just does tournament selection among those who are closest together, so that you're not getting into this chance where you've got 2 things that are on 2 different hills competing with each other when there could have been other partners that could have competed with on the same hill. And so the solution to this is so-called RTS, or restricted tournament selection. And in RTS, the idea here is that we have parents, A and B, and they end up producing offspring. So this is crossover and mutation, who we'll call A prime and B prime. And so we end up finding the individuals in a population window, W. So we could be the whole population or just some window, some smaller subset of the population who are most similar to A prime. And then we call that individual A double prime. And then we either keep offspring A prime or the individual we found A double prime. So I guess I can write that down here. So for A prime, we then find individual in population or subset of population most similar to A double prime in genotype space, and then keep A prime or A double prime based on fitness. And then we repeat for B prime and some B double prime. And that's restricted tournament selection. Okay, any questions about that? So that way we make sure that we try to, again, the goal here is to eliminate niche loss.
Sir, just what does A double prime stand for?
A double prime is an individual. So, sorry, there's a question online. An individual that we are calling A double prime. And so we find the individual in the population that is most similar to A prime, and I'm just calling it A double prime. It is an existing individual, possibly A prime's parent, but it may not be A prime's parent. So A prime is a new individual that we want to insert into the population. Before we insert in the population, we say, is there any other individual in the population or in a subset of it that is very similar to A prime? Call that individual A double prime, and then we compete A prime and A double prime against each other. Any other questions about that? All right, so the last one I want to mention, which is a more recent approach, is the SPGA, or the species preserving genetic algorithm for multimodal optimization. And in this case, we define some distance, hyperparameter again, that we'll call a species distance. And then we start with an empty set of conserved species. And then, kind of in an elitism sort of way, we're going to rank all individuals, all N individuals, by fitness. And we add, starting with highest rank, to our once empty set if no other already in is within the species distance over 2, sorry, of the individual. And then we perform GA operations on the population, but we are sure to copy, but we always copy excess into next generation. So this is a approach inspired by conservation efforts. And so it's this idea that there's some species that as they get, if they're species that are apparently important, then they get promoted into this special set of kind of elite species, and we make sure that we never get rid of them. And we don't ever add more species to it unless they're far enough away from existing species. And the hope there is that excess then starts accumulating a lot of decently performing species that are separated away from each other. And this approach seems to work pretty decently. So those are kind of the major, those are the, you know, the major sort of themes in niche preserving approaches for multimodal optimization. As we walk through those, I hope you can kind of like in the back of your head, sort of imagine what the computational complexity might be for these. So there's a more detailed analysis in the paper, but you know, as an example, like, you know, simple sharing, I hope you can see that it kind of has a complexity of n squared because you've got to compare every individual to every other individual, whereas clearing is a little closer to some constant multiple of n, or you know, at least, you know, it's you know, less than order n squared. And we could go down through this for each one of them. I mentioned that modified clearing is pretty ugly, I think, whereas it is, you know, 3 n squared. And so and because they do a second round of clearing is where the n squared comes from. So this is kind of an example where we're always tempted to do clever things, but when we really start talking about thousands of individuals over, you know, hundreds of generations, then these sorts of costs can add up and they can make your GA run really, really slow. In practice, RTS does very well and is decently efficient. So, you know, crowding approaches. So RTS has basically got a complexity of something like n times W, where W is the size of the window you look for competition from. So if you're looking over the whole in population, it's in squared complexity, it's just as bad as sharing. But if you say, I'm gonna just look for the top 5 or, you know, or 5 individuals or something like that, then you can scale that down. So you have a little bit of a speed accuracy trade-off that you can manage there. You can make the algorithm much faster, even though it may not be as accurate as doing the clearing. So RTS ends up being the kind of dominant strategy that we end up seeing in a lot of these multimodal optimization algorithms that are out there in nature, in engineering nature. So that's all I've got for you on niche preserving algorithms for this. If you got to go, that's fine. If you have questions, I'm happy to take that. Any questions? Make sure any online. Again, if you got to go, that's fine. I don't want to keep you too much. No questions online. So I'll see you guys over the weekend. Don't forget about your muddiest point on Sunday. There's also that mini project, I think 2 is coming up. It'll be due on Sunday. And mini project 3 is available. I think it's not due for a while. Oh, there's a concept check as well. So I think there's concept check 3A is due on Sunday as well. All right, any other questions online? If not, I will be heading out of the meeting.